Hi guys, so for those of you who were gone in class on Friday, what we're going to look at just reviewing transformations, and then we're going to look at those transformations applied to a new parent function. So the parent function that we're going to look at today is the cubic parent function, which is f of x equals x cubed. So what we're going to do to start is just see what this parent function graph looks like. So we are going to just plot some points. Well, if I plug in 0, 0 cubed is 0. If I plug in 1, 1 cubed is 1. If I plug in 2, 2 cubed is 8. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. So that helps you guys see the shape of this graph. So this is the cubic parent function. So you'll notice this graph, it's pretty narrow in the window that we have, just because if you think about how much it's going to increase for how little it has to, how much the y's are going to increase for how little the x's are increasing. Like our next point would be 327, then 464, and 125. So while it may look like this graph has an asymptote, it does not. The domain for this graph is actually negative infinity to infinity, as well as the range. This graph is increasing on the entire function, so left to right, my y's are always getting bigger. This graph does not have any decreasing intervals. This graph is positive everywhere that it's above the x-axis, which is from 0 to infinity. This graph is negative from negative infinity to 0. Symmetry, so this actually is an odd function. It has origin symmetry. So if you remember what we said origin symmetry looks like is basically if I reflect this over the y-axis and then also over the x. So if I take one and I flip it both ways, flip it over the x and then flip it over the y, or flip it over the y and then flip it over the x. Extreme on this graph is actually something that can be missed. So this little bend in our graph here, that is actually not a local min or max, because remember, local mins or maxes are where your graph changes from increasing to decreasing. And this graph does not change from increasing to decreasing. It's increasing on the entire function. So my extrema here, there are none. No local or global mins or maxes on this graph. Now what it does have, that point at 0 where your graph kind of bends, that is called our point of inflection. And what that means is that your graph is changing from concave up to concave down. So your graph is concave up at that point. Your graph is concave down for the rest of the graph. So that point of inflection is what we have right there at 0, 0. End behavior, so we write our two statements. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. All right, so what we're going to do now is we're just going to review our transformations and just look at what those transformations look like on the cubic function. So f of x minus h is a shift to the right. F of x plus h is a shift left. If b is in between 0 and 1, that is a horizontal stretch. Remember, it's opposite. B is greater than 1, horizontal compression. And then the negative inside is they reflect over the y-axis. So what this will look like on our cubic equation is almost exactly what it looked like on our quadratics. The only difference is that it's cubed instead of squared. So all of the horizontal transformations are happening inside the parentheses. And those are my horizontal transformations. Again, inside the parentheses is all of the horizontal stuff. Just for every function we do, the parentheses are going to look a little bit different. All right, second half has all the vertical transformations. So plus k is up, minus k is down. If a is between 0 and 1 and it's on the outside, that's your vertical compression. A is greater than 1, that's your vertical stretch. And then negative on the outside is they reflect over the x-axis. So for a cubic equation, that would be x cubed plus k. X cubed minus k. So again, outside, away from those parentheses would be our vertical changes. Now, one thing you may notice your reflection over the x and your reflection over the y really look like the same thing, because on this particular function, f of negative x is the same thing as negative f of x. That's because it is an odd function. It has that origin symmetry. All right, and the last thing just to consider is if you have more than one horizontal transformation, you want to factor out whatever that b value is, or that negative, so that it makes it easy to see what that shift is. And then when we have it in this form where that b is factored out like that, the hk that's on there is your point of inflection. All right, so let's look at this actually applied to some cubic functions. So on this one, the transformations, we're going to list those first. So this graph has gone right 3, down 4, reflected over the x, and vertically compressed by 1/2. So in order to sketch the graph, the first thing we want to do is we want to find the point of inflection. Well, if it's gone right 3 and down 4, that is our point of inflection. Then from this point, how you graph your equation is really up to you. There's a couple different methods you can use. If you like to plot points, you can go ahead and pick certain x's, plug them in, and see what y's you get as a result. So if I want to take 4 and plug that in and get the corresponding y, I could do that. I do suggest, though, you plot the point of inflection first. That way you get some good points that are easy to see. So I would pick something to the left and to the right of that point of inflection. Now, the other way that you can do this, the way I prefer to do it, is I like to use transformations, and I like to see how this graph has changed from the parent function. Well, the parent function from the point of inflection usually goes over 1 and up 1. It usually goes over 2 and up 8, left 1, down 1, left 2, down 8. And that's normally how we move from the parent function's point of inflection. Well, our point of inflection is now in a new place. And what's changing now is that we have that compression and that reflection over the x-axis. So what that means then is that from my point of inflection, instead of going right 1, up 1, I would go right 1 and down 1/2. I would go right 2 and down 4, left 1, up 1/2, left 2, up 4, from the point of inflection, because my y values, I'm getting multiplied by a negative 1/2. So again, from the point of inflection, right 1, down 1/2, right 2, down 4, up 1.5, left 1.5, left 2, and up 4. And that's enough points to see your graph. Domain on this function, negative infinity to infinity, range as well. And then this graph, since it's been reflected, it is not increasing anywhere. It is decreasing on the entire domain. All right, now this next one, again, if there is some sort of a b value, we want to factor that out. And not out of the cubed, just moved aside to make it clear what your point of inflection is. So now that that's out there, we can tell that this graph has gone left 2 and up 1. So the point of inflection is at negative 2, 1. We can also tell the transformation, that 1/3, that is a horizontal stretch. So now to graph this, if I look at my parent function transformations, from the point of inflection, right 1, up 1, right 2, up 8, left 1, down 1, left 2, down 8. What's different, though, is that I have that horizontal stretch. That horizontal stretch is going to affect the x-coordinate this time. So, and since it's a stretch, I'm going to multiply those x's by 3. So 3, 6, negative 3, negative 6. So from that point of inflection, right 3, up 1. Right 6, up 8. Same thing, left 3, down 1, and left 6, down 8. Connect my dots, and that is my graph. All right, domain on this is negative infinity to infinity, and range is negative infinity to infinity. As x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. All right, so that's really it for these cubic functions. What you really need to do, again, is just be able to identify that point of inflection, identify your transformations, and then from there you can sketch points either by plugging in points or by just seeing how your parent function has changed. Just remember that Desmos assignment that's on Schoology is a grade. So you really need to finish the last 4 slides on that and write the equations of those graphs.